a e to the minus 2x dx. But that we can integrate, right? I'm just going to do it. I'm going to pull the a out, right? There, I pulled the a out because it's a constant. And when we integrate, we get minus 1/2 e to the minus 2t plus 1/2 e to the 0. U substitution divides by minus 2, right? Make a u equals minus 2x substitution there. And so, well, as t goes to infinity, this piece drops out to 0, right? And what else? What do we get? You're all good. I'm just zooming out a bit. So e to the 0 is 1, right? So we got ourselves an a over 2. That's equal to 1. So therefore, pick a equals to 2. So we put a equals to 2, and we've got an honest to goodness probability distribution. Woohoo! Yep.
Why is it equal to 1?
By assumption, because the sum of the probabilities has to be, 1. Now, if you wanted to figure out the probability that you'd find x between, I don't know, 1 and 2, you just integrate this function from 1 to 2, and whatever that is, that's the probability you're going to measure x between 1 and 2. What's different about this than like the probabilities maybe you studied in high school or something before you had calculus? What's the difference? Yeah.
I feel like there's a finite amount of possibilities in previous situations, whereas here it's like a whole range of possibilities.
Yes, I think that's exactly it. Before you tend to focus on examples where you have a finite number of possibilities. The state space is finite. You have a couple of dice, you roll them, right? And then there's 36 possibilities. So if you've got 3 dice and you roll them, you've got however many 6 to the third is possibilities, right? You're making a 4-letter word. How many different 4-letter words are there? I don't know. If we're allowed repeats, 26 to the 4th, right? If we're using the English alphabet, there's 26 to the 4th possible 4-letter words. Anyway, but all of these different counting things, they all start from, like you said, some sort of finite totality of possibilities. Whereas here, what connects to? Well, it could be any real number, right? So there's an infinite number of potential outcomes for x. And so this context of statistics or probability, I should say, is when we're talking about a continuous random variable. So here x is what's called a continuous random variable. And for continuous random variables, we need calculus to describe the statistics. The most famous example of this is the Gaussian distribution. Do you guys know the Gaussian distribution? I saw, so that's this one. I'll do it down here. So, do it over here. So, if you, usually speaking, if you grade a test with enough people in it, what do the grades look like?
A bell.
Well, excuse me. A bell, right? So if is that the right way to say it? I think I'm graphing number of people with grade, and here's grade, And so you'll get something like, we don't usually give grades less than 0. Not with my current syllabus anyway, but you get something like that, right? In the middle, you've got this average, right? But this isn't really what you do. I mean, really, what you have to do is you have to bin the data, and you say, well, how many people have a grade of a certain range. You know, you make a histogram, and the thing is, if you have enough data, the histogram starts to approximate more and more this bell-shaped curve, which is defined in terms of the Gaussian function. I have this in the notes. Let me show you. Aw, man. Don't you do that to me. What are you doing? So, boop, 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 boop. So this is actually something I learned in Math 115 of all places. I'm sure they were really, really excited to see Calculus 2 in their course last semester. But maybe you'll like it more, I don't know. So listen, there are a caboodle of examples in the notes that I have not got to. And this is true of pretty much every topic. So if you read my notes, you will get more than I have shown in class, believe it or not. And so like here is the definition of a probability distribution. Like I just told you guys, I wrote that on the board, right? But what I didn't write on the board yet was that the mean value, what you do is you integrate x times f of x, right? So I think you have a homework problem where I ask you to calculate the mean value of something, right? So I'm not being mean, just asking you to take x and multiply it by the probability distribution and integrate that thing, all right? And here, I work out an example much like I just did, but with a slightly uglier thing. It actually had an integration by parts in it. Look at that. Ooh, fancy. And then I have another example where I have an evil triple case probability of distribution, and then I actually select A and B so that it makes it continuous. How do you make it? If it's continuous, that means that the different cases have to glue together like smoothly, right? This one I just gave you, the one we have, I just covered up with the board, is not continuous because it jumps from 0 to a half as you go from negative to positive values, because e to the minus 2x times 1/2 starts at a half. So there's a discontinuity in that probability distribution. And it's probably the one we just solved in class. Like, honestly, guys, I'm not sure that actually fits any kind of real random variable that you could ever come up with in nature. Probably not. But this one is the most famous. So this is the Gaussian distribution. And so mu is the notation for the mean. And so like to give you so what's going on here is you've got the average, right? And then, oh, fine, it's here. I'll use it like that, all right? Standard deviation, it tells you how spread it out it is, right? So basically, the story is this. If you go this much right here, something like that, this is mu plus sigma, right? And then over here is mu plus 2 sigma, and so forth, right? And for example, if you go plus or minus 3 sigma, one side to the other of the average, the area that you get under this, the Gaussian curve is something like 98%, right? And there are these rules of thumb that you learn in your statistics class. But there's something interesting. So to calculate the area, to calculate the probability due to the Gaussian distribution, what would you have to do? You'd have to integrate. You have to do this integral. Whew, look at that. E to the minus something squared. I mean, this sigma and the mu aren't so concerning. Just pull it back to this. What's the integral of e to the minus x squared? Like we have not covered it, and the reason we have not covered it is because it's not accessible by elementary means. It is an integral which cannot be done using integration by parts, partial fractions, trig substitution, any of these things, because the antiderivative of this function, while it exists because it's continuous, it's not expressible in terms of elementary functions. Elementary functions being the lexicon of functions that we use: sine, cosine, exponential, algebraic functions, all right? There's a trick in Calculus 3 to calculate the integral from minus infinity to infinity of e to the minus x squared. You change to polar coordinates, and you can show it's related to like the square root of pi. This is very sneaky. So the point is, you can calculate it, but it involves Calculus 3, and it's really a very conniving calculation. But there's something that should bother you about this, which is that in Math 201, which is algebra-based statistics, we make people calculate the probability that a certain random Gaussian random variable be found in a range of values. That means that they're integrating this function, which you guys can't integrate despite your many countless hours of work already, right? How is that? How do we achieve this? It's a sneaky trick. So what you do is you make a substitution. See, you introduce what's called z, which we call the z-score. Z is x minus mu over sigma. When you make this substitution, this random general Gaussian distribution simplifies back to this. Notice that it simplifies back to this for any choice of average, for any choice of mean, and for any standard deviation. It always goes back to the same standard normal distribution. Which means that if you make a table of values for the integrals of this over certain ranges, you can calculate the area under that for any choice of mean or standard deviation. That is why 201 students can calculate these areas, because it's a U substitution. Actually, it's a Z substitution. It's perhaps the most interesting U substitution that there is. Now, I don't introduce this in Calculus 1. I'm like, oh, well, U substitutions are interesting because of the Z-score. Like, no, I would not say that, because I would have to talk to them about improper integration, which would be kind of out of bounds in Calculus 1, right? I think, usually. But anyway, I just think it's interesting. And then this, you'll find graphs of this. Like if you look at any introductory math text, they'll have pictures of showing that you can take the wherever standard distribution, and through the z-score mapping, you convert it back to the mean is 0, and it's symmetric about the origin like this. So here you've got z-scores, whereas over here you had what you're actually interested in, which is x. So by making this mapping for the z-scores, you can convert it to a standard thing, which you can then look up in a table, which I hand out during my Math 115 test. So. And then they make arbitrary definitions, like if you're beyond, so like if you're between z-score, so being between z-score minus 3 and 3 means that you're within 3 standard deviations plus or minus of the mean. There's a 99.7% chance that your data should be in there. So if you're beyond 3 standard deviations, then they define it to be an outlier. So those are pretty rare. However, fun fact, in physics, there have been any number of false discoveries that have been announced in the science journalism industry. Like, oh, we found such and so forth, and then what was the certainty about it? Well, it was we had 3 sigmas confidence. It's outside 3 standard deviations of the statistics, and there have been several things that have turned out later to be false and unreproducible, because 3 standard deviations is not enough for theoretical physics these days. You need at least 5. If you get 5 standard deviations, then you're pretty confident that you're not looking at an outlier if it's within 5 standard deviations, your result. Anyway, that's it. So, hey, listen. So you asked me about like iteration. We can do that next time. We can do whatever we want next time, because I have covered the material. This is it. So like tomorrow and Monday, your questions is what we have. All right. Uh-huh. Oh, yes.